Hello friends, in this lecture we will study parallel and transverse magnetic field effect on charged particles or motion of charged particles. In the previous two lectures we have studied this behavior of electric field or effect of electric field on charged particles, and especially we have concentrated for electrons. The behavior of magnetic field is entirely different than electric field, and many new results we will discuss, interesting results we will discuss here. In this lecture, we will study the magnetic field effect on when particles are at rest, then magnetic field effect when particles are moving, and then possible applications, mathematical background, and basic descriptions, and finally the applications of this. In the previous lecture, we have studied details of motion in longitudinal magnetic field and brief idea of perpendicular magnetic field. How the perpendicular magnetic field can rotate the charged particles and how the rotation is different for negative and positive. Today we will discuss mathematics of this in detail. Let us consider the case of an electron of mass m and charge q entering in a uniform magnetic field B with its initial velocity Vx perpendicular to the field. The magnetic field is considered to be given in a direction into the plane. We have shown in the previous figure the magnetic field into the plane. You must remember the cross represents something moving inside and the dot represents something moving outside towards you. We have taken this analogy from arrow. The dot represents arrowhead. If you see an arrow from the top side, you will see only dot. But if you see the arrow from the bottom side, you will see a cross there. The magnetic force can be calculated and can be written as QVXB. Here we have taken velocity is perpendicular to B. So QVB sin theta will be equal to QVB. Sin theta will be 90 here. This is our magnetic field. This has a constant magnitude. This force can't change the magnitude of electron velocity, but can deflect the electron. We have discussed this in the last class. It can only change the velocity. It can only change the directions. So, this we can use for analyzing the path that the velocity cannot change and the electron will be deflected continuously along a curved linear path. And this is the reason why you will have a circular path. The tangential component of FL will be 0 as FL and Vx are mutually perpendicular. Therefore, the normal component will be equal to FL and this will always act perpendicular to Vx at each point. Therefore, FL is a centripetal force, and this centripetal force FL is given by mv square upon r. In our case, v is Vx, so mvx square upon r. We have already calculated this FL as qvxb. If we equate these two, then we can calculate the value of r. This r is giving you the idea of radius. Now the whole thing is little bit clear. The particle is entering perpendicular to magnetic field, and particle is deflecting due to this magnetic field in the third direction. Since it can only change the direction, no velocity, it follows a circular path and behave as a centripetal force. If we use the Newton law of motion of centripetal force, we can obtain the relation, and we can obtain the radius, with which radius the particle can move. This equation gives lot of things. Suppose velocity is high, then r will be high. For higher velocity, the radius will be high, bigger circle. For a smaller velocity, smaller circle. This is also depends on mass. If mass is different, suppose you are having isotope, we will discuss this thing later also. Isotopes, I think all of you are aware of the isotope word. Having same atomic number but different masses. In chemistry we have isotope term. Some element have different masses. Carbon have different masses. C12, C13, C14 and so on. So this can be separated using this method, because if you are having the element is same but mass is different, you will get different circles. The velocity is different, you will get different circles. And we will also see this in the coming lectures and slides. Then this property can be used at various places. If we assume all other parameters constant, Vx is constant, M is constant, B is constant, Q is constant, then R will be constant. The path followed by the electron will be a constant circle. The electron will describe in a circular path a plane perpendicular to magnetic induction lines. The sense of rotation will be clockwise if magnetic field directed into the plane. For a positive charge, the sense of rotation will be anti-clockwise. We can check the direction of magnetic field using Fleming's rule. I discussed in detail in the previous lectures. You can refer to those lectures how to calculate the direction. And we have shown the direction in the figure. The time period of one revolution can be calculated. As we know, the time period is equal to distance covered in one rotation divided by speed of the particle. If the particle is taking circular path, then in one rotation, the total distance covered will be 2 pi r. If the speed of the particles we have taken Vx, then this can be done as 2 pi r over Vx. Now, we have already obtained the value of r in the previous slide. This can be put here, mvx upon qb. If we put this slide here, the answer will be 2 pi m upon qb. Vx is cancelled out here. This also shown a very important result. The time period of one revolution is independent of velocity of the particle. It only depends on mass q and v. If we have chosen same particles, same mass, same charge, and magnetic field is same, the time period will be constant. The frequency of revolution can also be obtained using this. Frequency is reciprocal of time period 1 upon t. Then this will be qb upon 2 pi m. The frequency indicates that the time period and the frequency both are independent of velocity of the electron and radius of the path. Vx and r exits each other in such a way that t and f stays constant. Again, I am saying we must underline these things. What is this? The velocity of the electron and radius of the circular path adjust such that t and f stay constant. Why I am saying divide this? This can be asked in the exam. Show that. You can show this. We can also check this. Slower particle move in smaller circle while faster particle move in larger circle, so as to keep the time period constant. These type of things can also be asked. How show this? Show. How can you show that the T and Fr stays constant? You can show by here. T and F are constant and it's not depend on V and radius because it is not in the formula. It will cancel out previously. Similarly, you can also see time period constant. Motion of charged particle projected at any angle into the magnetic field. If the electron of mass m and charge q with a uniform velocity enter with velocity v enter in uniform magnetic field with some angle. Initially we have discussed 90 degree. Now I am saying some angle. It is more general formula. Then the magnetic field suppose in that direction, the electron velocity can be resolved into two components, Vx and Vz. The component of velocity parallel to magnetic direction, that will be V cos theta, that will be not be influenced by the field, as we already discussed. If something is moving in same direction or the component is there, that will not be affected. So FLZ will be Q Vz cross B should be equal to 0. So the velocity of electron continues to travel along the field line with a velocity Vz is equal to V cos theta. There will be no change. However, the another component, that is Vx is equal to V sin theta, give rise to force on electron, and that force will be QVxB or QVB sin theta. Under the action of this force, the electron tend to describe a circular path, and the radius of this path is given by mvx upon qv. We have discussed this. In place of vx, you can write mv sin theta upon qb. We can also calculate time period of one revolution. 2 pi r upon vx. Why vx only? Because another will not affect. So we have taken only one component. If we taken this component and we put the values, Vx can be written as V sin theta, R can also be written as mv sin theta upon qb. Again, this will cancel out and it will left with q pi m upon qb. So here we must mention, if you are working with particle is moving with some angle, then we have splitted our problem into two parts, one which is parallel to, one which is perpendicular to, and by this we have solved these values. Most of the time the derivation is same. The resultant motion of the electron is obtained by superposition of uniform translation motion parallel to B and uniform circular motion normal to B. The resultant motion is along helical path with the axis of helix in the field direction. Now it is moving in circular direction but moving forward, so it will create a helix in the forward direction. The pitch of the helix is the distance covered by the electron along the field direction in one revolution, that is called pitch. We have also calculated pitch in screw gauge, the same definition we have given, in one distance traveled in one circle. And the pitch can be calculated as Vz into t, distance traveled, or V cos theta into t. And you can also put the value of t here. So this will be 2 pi m V cos theta upon qb. So we can calculate pitch. Now we observe three behavior, one which is undeflected, second which is in circular direction at the same place, and third, the particle is moving in the forward direction with some helix. Magnetostatic deflection. If a uniform magnetic field is formed over a length L, then it is assumed that the magnetic field lines of force are directed into the plane of paper and the electron beam having velocity Vx entered the magnetic field in a direction perpendicular to the field direction. The electron beam bends towards the arc, radius is radius r. After emerging from the field, the beam continues to travel in a straight line and strike the fluorescent at Q. This is an application part. A particle is moving, you pass the particle through a certain length, then move outside this. In the particular magnetic field, it will move in a circular direction, it will bend in a circular direction of radius r. Then whenever the length is over, the magnetic field length is over, it will move in the straight path. So this can be calculated for various applications. The circular are subtend an angle theta at P. So AB and AC are the radii of the circle having its center at B, and AO and OQ are tangent to the arc AC. Using this, we can calculate YQ, which is equal to Y is equal to T tan theta. D is the distance of the screen from the center of the magnetic field. Theta is small. If theta is small, you can write Y as arc upon radius. So D is AC upon R or DL upon R. Now we know the value of R. If you put this value, you can calculate Y. The value of Y will be DLB under root of Q 2MVA, because we know the value of V and we have put this value here. So you can study the displace actual deflection using this. Actually, this is the application part, whatever we have learned in the previous class. We can also define the magnetic deflection sensitivity. deflection upon magnetic field. The deflection by a unitary magnetic field is called magnetic deflection sensitivity, and this is equal to dlq upon 2mva. The deflection sensitivity is inversely proportional to the square root of accelerating voltage. Now, in the next lectures, we will study the applications of these things. Till today, we have studied deflection due to electric fields, deflection due to magnetic fields. Now, we will use these deflections in many applications. Thank you and take care.